Okay, so in the previous video we saw the notion of uniform continuity, and we have also seen that a uniformly continuous function maps equivalent sequences of real numbers onto again equivalent sequences. We can now use this fact to show that a particular function that we have already considered is not uniformly continuous, and that function is this one. This is not uniformly continuous. On its domain. And the reason is this: we are now going to consider two specific equivalent sequences in this domain, but the F images of those sequences will not be equivalent. Consider the sequences one over n, where n varies from 1 to infinity, and 1 over 2n. We of course do not start the index n from 0 because then it will be undefined. So we start n from 1. Now it is clear that both these sequences are in this set. That means in each sequence all the terms are elements in this set. Oh, we should mention that. Consider these sequences in 0, 2. They are equivalent because of that result. This limit is equal to 0, and in fact let's also write what that result was. Lemma 997 by lemma 997. However, let us now see what happens to the F images of these sequences. Note that one over n is actually, because we are just going to take the reciprocal of the input, it is the sequence of all positive integers. And similarly, f of 1 over 2n is the sequence of all positive even integers. But these two sequences are not equivalent. But these are not equivalent since the limit of n minus 2n as n approaches infinity is not equal to 0. Actually, the limit in this case does not exist at all. So, no question of it being equal to 0. Again, by this lemma, because of this fact, these two sequences are not equivalent. And that proves that our function cannot be uniformly continuous by proposition 998. So, f is not uniformly continuous on this domain open interval 0 comma 2. So in this way, using this proposition way, it's just a matter of finding two appropriate equivalent sequences whose images under the function are not equivalent. Then the function cannot be uniformly continuous. However, using the proposition to show that a function is uniformly continuous may be slightly problematic, because in that case you will have to consider any pair of equivalent sequences and show that the f images of those sequences also are a pair of equivalent sequences. But if you want to show that something is not uniformly continuous, then this is a nice way. Alright. Now, just like uniformly continuous functions preserve equivalence of sequences, they also preserve Cauchy-ness of a sequence. That is the next result. Okay, but before that there is another example. Let's just see that also. That Cauchy thing is coming afterwards, but before that we have this example. Let us now consider the ordinary square function on the entire real number set. Is it uniformly continuous? It turns out that it is not uniformly continuous, and the situation is somewhat like that example where we considered 1 over x, but in the open interval 0 comma 1. As x approaches 0, the situation of continuity, the continuity gets worse. Something like that happens here also. As you go far away from 0 in this case, I mean, you of course know what the graph of this function is. It's the parabola. So as you go far away from x, either on this side or on that side, the situation of the continuity, the status of continuity gets more and more problematic. Okay, for a fixed epsilon, the more you go on that side or the more you go on this side, your island of stability becomes smaller and smaller. So this is not going to be uniformly continuous, but of course we are going to show that just like this one, using two sequences of real numbers which are equivalent, but their f images will not be equivalent. Consider the sequences. Well, one of them is the sequence of all positive integers, and the other one is n plus 1 over n. Since this limit exists and is 0 by lemma 997 this and this are equivalent. Now we need to see what happens to the f images of these sequences. That is, the sequence terms will get squared. Now, and we need to see if they are equivalent. So if we take the square of n plus 1 over n and subtract from that the square of n, because after all we need to be able to use this lemma to see whether these two sequences are equivalent. So we are considering the difference. Now if you expand and do all the calculations, of course n square and minus n square, they vanish, and you will have a 2 here. 2 times n times 1 over n is 2, and an extra 1 over n square. And this approaches 2 as n approaches infinity. So it does have a limit, but that is not 0. Hence by lemma 997, the sequence f of n and f of n plus 1 over n are not equivalent. So by our proposition, the square function is not uniformly continuous on R. Proposition 998. I have I have already said this before, but again I am repeating. If you wish, you may choose to not write this on R on 0, 2. If only one function is involved and it is pretty clear what is the set on which we are verifying its uniform continuity or lack thereof, then this on that set, that part can be omitted. Alright, now next comes that effect of a uniformly continuous function on a Cauchy sequence. So this is the next result. And the proposition basically says this: X is a subset of R, non-empty subset of course, and f is a function from X into R, that is uniformly continuous on X. I'm just writing what the proposition says. I'm not writing things formally. There is no need. The main thing, what it ultimately says, that's what matters. Let So now we are going to consider a Cauchy sequence of elements in the domain X. Let Xn, for some reason the author has started n with 0, but you can put any integer here, does not matter. Let this be a Cauchy sequence in X. Then the F image is also a Cauchy sequence. Now, using this new criterion, we can go back to one of the functions, namely that 1 over n function, and using this result, we can again show that that function is not uniformly continuous on open interval 0, 2. And that is example 9913. It's a simple thing. Instead of using the criterion involving equivalent sequences, we are using this criterion. Oh, and note one important difference between this result and that equivalent sequence result. Here, if f is uniformly continuous, then the image of a Cauchy sequence is also Cauchy, and that's it. However, in that equivalent sequences formulation, it was if and only if. Okay, so that difference is there. So using this, we can only prove that some functions are not uniformly continuous, like what we are going to do here. So our function was just this. And the sequence we are going to consider is that simple 1 over n sequence. That's it. We already know that this is a Cauchy sequence in 0, 2. You see, moreover, all the elements here, all the terms in this sequence actually belong to 0, 2. However, if you had 1 here, then that would not be the case, because the first term of the sequence in that case will not belong to this set. But we have taken 0, 2, so no problem. But what about f of 1 over n? This is nothing but the sequence of positive integers, and this is not a Cauchy sequence. The author does ask us why. Well, the reason is that the difference between any two terms of this sequence is at least 1. You cannot make that difference less than 1. So if you cannot make the difference less than 1, how can you make the difference less than epsilon for any given epsilon? And that's why this is not a Cauchy sequence. So by what was that, 9912, huh? Yeah, so by proposition 9912, yes. F is not uniformly continuous. So you now have got another tool to show that something is not uniformly continuous. Now there is a corollary to this, to that 9912, and that corollary is this. You may be noticing that I am not saying anything about the proofs of this result. That's because the proofs, all these proofs are exercise problems. So we will solve them in the exercises, in the community section. Right now we just see the results and their applications and the examples that illustrate these results. So this is corollary 9914, and here the claim is this. Like before, X is a subset of R, a non-empty subset, and F is a function with X as its domain, R as its range, and that is uniformly continuous. On X. Okay, and there is an adherent point of X, X naught. Then the limit of f of x as x approaches x naught in E, this limit exists. Okay, so that is the claim of this corollary, and this also we will prove in one of the exercise 4 actually. And there is one more result related to boundedness of a function. Let's see that also. Boundedness of a uniformly continuous function. You see, boundedness is not always necessary for continuous functions. We have already seen that. For example, in the very beginning, we considered that function reciprocal function 1 over x, and where the domain is 0, 1. It is a continuous function. It is continuous at every point in its domain, but it is not bounded. The value goes without any bound, it grows like that. Okay, so boundedness is not necessary. Boundedness does become necessary if the interval is a close bounded interval. Alright, but now we are going to see that we can also have boundedness as a necessity if the function is uniformly continuous. Okay, the domain may be anything, but the function is uniformly continuous. So the next result is about that. Again, X is a subset of R, and F, I need ink, okay, just give me a moment. Actually, you see, while going through Terence Tau's analysis book, we almost never fail to notice one thing. At first we get frustrated to see so many exercises contain proofs of key theorems. Okay, we get frustrated seeing this. On the other hand, on the positive side, we quickly notice something else. You see, when we go through a mathematical text, we get definitions, we then get results, and then there are proofs, corollaries, there are proofs. So we naturally get stuck with the proofs. And that creates a kind of we understand the proofs eventually and we move on, but it impedes us. Instead, if we have just the results like this, and first we go through the results themselves, digest what they are trying to say, digest their meaning, and then see how those things are happening in the application. Application means in the examples. And then only one after another we go to the proofs of these results. I think that way of going through the things more solidifies these notions. I mean, we can connect them more quickly and we see the proofs afterwards. This is a very nice way of remembering things also. But anyway, you can practice this even in texts where proofs are available. Say, on a first reading, you ignore the proofs altogether. You give the text a global reading, maybe 2 or 3 times. You then get a rough idea of where the things are, what the things are, and then only you go to the proofs. This is uniformly continuous on X. Okay. Now if E is a subset of X such that E is bounded, that means E is contained in some open interval whose boundary points are real numbers. Okay, then E is bounded. E is bounded. Then the F image of E is also bounded. Uniformly continuous functions preserve boundedness of sets. And this also we are going to prove in one of the exercises. And finally, for today, let us see this extremely important result, which says that if we take a special kind of domain, the kind of domain we have already taken for continuous functions, that is closed bounded intervals, then we have seen that we have the maximum, the extreme values, also intermediate values. Those things we have already seen. But something else also happens when we restrict the domain to be a closed bounded interval for a continuous function. Then it automatically becomes uniformly continuous as well. Okay, uniform continuity is stronger than continuity, but if our domain is like that, then continuity implies uniform continuity. So the next, it is a theorem, is about that. And the statement is basically this: A and B are real numbers where A is less than B, and F from closed interval a comma b into R is continuous, ordinary continuity. This condition makes sure that this is a non-empty subset of R. This is continuous, then F is uniformly continuous. But if we change the interval, then of course we know that the conclusion is no longer necessary. For example, if you take the reciprocal function on open interval 0, 1, it is continuous there but not uniformly continuous. However, if you take reciprocal function, well, you cannot take closed 0, 1 because it's 1 over x. Say you take 1 over x function on the closed interval 1, 2, there it will have to be uniformly continuous despite having a graph like that. Now the proof of this is not an exercise, it's there in the text and we will do it, but not today. In the next analysis video, we will do this proof. And that's just it for tonight. Tomorrow, tomorrow we are going to upload that calculus video that I was supposed to do this Saturday. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.